Hi, welcome to a new edition of H.E.L Explains with your host, Dr. Mario Torres Rodrigo. And today, when I was deciding what topic to talk about, the inspiration struck me. I could actually combine two of my main passions on this video. On the one hand, being the applications leader here at H.E.L, calorimetry is such a fundamental interest of mine. But also, on the other hand, being Spanish, coffee, it is such an intrinsic part of my culture. So I decided, why not combining both in this video? So I guess that the first thing that we want to ask ourselves is what kind of calorimetry concept we can evaluate using something as simple as a coffee cup and a thermometer, and the answer is enthalpy. And enthalpy might sound like one of these very complex words and very complex concepts that physicists and scientists talk about all the time, but actually enthalpy is all around us and is such a fundamental part of our lives. Enthalpy is going to determine how we can cook our food, how we can brew ourselves a cup of coffee or a cup of tea. And to give you an example of what enthalpy is, let's just imagine that we are in the middle of winter and our house is brisk, is for example at 16 degrees. And we really want to make our house more habitable, and we decide to crank up our heating. Let's imagine that, for example, we have a gas heating system, and what is going to happen when we turn it on is that we are going to have a combustion reaction happening. We are going to have, for example, methane, which is the main component of biogas, that is going to be reacting very quickly with oxygen, and in this reaction heat is going to be released and is going to be accumulated in our heaters. As the house is warming up, some of the heat from our heaters is going to be dissipated into the surroundings, into the room. And what is going to happen then is that the enthalpy inside of the radiator is going to be lost to the surroundings, which are going to be gaining some of this enthalpy. So yeah, what is enthalpy? Enthalpy is the total energy of a system, which includes the internal energy of the system and its pressure and volume. And it's all represented by the following very simple equation. H, the enthalpy, equals the internal energy U plus the pressure P times volume. And in the case of our coffee cup calorimeters, we are going to be regarding it as a diabatic calorimetry. This means that because of how insulating styrofoam is, no heat is going to be lost from the cup to the environment, and no heat from the environment is going to go into the cup, which means that if there's any kind of change inside of the mug, is going to come from within the system. So if we go back to the very simple equation I showed before, we have the enthalpy equals the internal energy times pressure times volume. And if we have that the volume in our cup is not going to change, it's going to remain constant, that means that this part of the equation is going to be zero, which means if there are any changes in our enthalpy, they are all going to be linked to the internal energy of the system. So how can we measure this? Well, we go back to having our styrofoam cup, and we are going to mix certain reagents inside, A and B, and on the chemical reaction, they're going to be producing other two products, C and D. If we assume that this is an exothermic reaction, as the chemical reaction is progressing, it's going to generate energy. The energy then is going to be transferred into the water that is contained inside of the cup, and this is going to make the temperature inside of the cup to increase. So with all this information, how can we study the change in the internal energy of the system? Well, we have this equation here in which the heat of the reaction is going to be equal to the mass of water that we have inside of the cup times the specific heat of the water times the temperature at the end of the reaction minus the temperature at the beginning of the reaction. The heat capacity of the water is going to be how much heat the water needs to absorb in order for the temperature to change. And the result of this equation is going to be the change in our enthalpy. This was a great example of homemade calorimeters. However, professional calorimeters look slightly different. They look something like this. And in the picture, what you can see is one of the similars that we manufacture at H.E.L. And I'm going to spend a good couple of minutes trying to explain how we can learn calorimetry using this kind of instrument. So there are a number of ways in which we can analyze calorimetry, and the most extended one is heat flow. In this case, the temperature in the reactor, so inside of the coffee cup we had as an example before, is going to be controlled by a jacket, so a layer that is going to be around this reactor and is going to contain a fluid. There's going to be another layer outside that is going to be the insulation, so basically the styrofoam that we had on the coffee cup. So the temperature inside of the reactor is going to change as the chemical reaction progresses. And the energy produced or absorbed by the reaction is going to be Q, which is going to be equal to U times A times the temperature inside of the reactor minus the temperature in the jacket. U is going to be the coefficient of heat transfer in the system, so basically how much energy can the reactor absorb, and A is going to be the part of the reactor that is going to be in contact with the water, so it's what we call the wetted area. But there is even a more simple way to get the energy and a faster way to calculate the energy produced in the reaction, and this is power compensation. In this case, the fluid in the jacket is going to be at a different temperature than the temperature inside of the reactor. And we want to keep the temperature stable, so that means that as the reaction is progressing, it's going to either produce or absorb energy, which means that if it's producing energy, the power supply that is heating the jacket has to stop, so the temperature inside of the jacket doesn't go over. The energy that the supplier is not giving the jacket is going to be the same energy that the reaction is going to be producing. So the messages I want you to take home from this video is that enthalpy, despite of being such an alien concept, actually is present in our daily lives. Calorimetry is a very powerful tool that allows us to characterize this enthalpy. And finally, that there are different ways to characterize enthalpy. And that's it from me. My name is Dr. Mario Torres Rodrigo, and I'm the applications leader here at H.E.L. So if you have any comments, if you have any questions, please just reach out for us, talk to us. Thank you very much.